The success of a mission depends on comprehensive testing of a spacecraft's instruments. All vehicles that travel beyond Earth are exposed to the harsh environment of space. Could a mission fail if a small particle called a micrometeoroid punched a hole in the side of a spacecraft? What about one of its instruments? In this test, a marksman shoots through a duplicate of an instrument grid. The resulting square hole caused by the gunshot simulates the damage caused by micrometeoroids in space. This test helps mission scientists study the potential risk of micrometeoroids hitting a spacecraft. NASA's Discovery mission Genesis launched in August 2001. Its spacecraft traveled 1 million miles sunward. After a 2.5-year sunbath, Genesis is scheduled to bring back minute pieces of the sun. Scientists will learn more about the elements that were present at the time our solar system formed. What important elements will scientists examine in the returned samples? They will measure isotopic compositions of oxygen, nitrogen, and noble gases. We know there are isotopic variations of the elements in meteorites, comets, lunar samples, and planetary atmospheres. Studying these solar wind samples will give scientists a better understanding of these variations. They will reveal the building blocks of our solar system. How will Genesis collect these samples? By using the sophisticated instruments mounted on the Genesis spacecraft. The Los Alamos National Laboratory in Los Alamos, New Mexico, built important data-gathering instruments for the Genesis mission. Scientists at the laboratory have developed instruments to measure and collect different types of solar wind. In the extreme environment of interplanetary space, these instruments must withstand a broad range of temperatures and hostile conditions. Roger Wiens leads the Genesis work at LANL.
Los Alamos is responsible for 3 of the instruments on the Genesis mission. In fact, we're responsible for all 3 of the electrostatic instruments that interact with the solar wind actively. Those 3 instruments are the ion spectrometer, the electron spectrometer, sometimes called the monitors because they are checking in real time the solar wind, and then also the solar wind concentrator, which is a brand new kind of instrument. And we are also, in addition to those instruments, we are responsible for the science algorithm, the robotic logic that the spacecraft has, which takes the raw data from the solar wind as measured by the monitors, and it reduces that, tries to understand what regime of the solar wind or what type of solar wind is blowing, and then helps the arrays or commands the arrays to respond accordingly. And it also controls the voltages on the concentrator so it can give an optimal concentration of solar wind onto its target.
The sun pitches pieces of itself into its surrounding space. These pieces are called solar wind, and they come in 3 types. Slow solar wind is often associated with streamers visible during a solar eclipse. Fast solar wind emerges from coronal holes in the sun's atmosphere. Coronal mass ejections are explosive releases of material from the corona. The Genesis spacecraft serves as a catcher collecting all 3 types of solar wind samples that will give us clues about the formation of our solar system. However, scientists are especially interested in the data from the fast solar wind.
The most important sample to us is most likely the sample of the fast wind, because from our measurements in the past of the solar wind, the fast flows are most uniform in elemental composition, in the charge state composition of the ions, and in general in the density itself. There's probably less variability and a more uniform process that pulls out solar wind in the fast flows. That, we believe, will be our best sample from Genesis.
There are monitors on board Genesis that serve as the eyes and ears of the spacecraft. The Genesis Ion Monitor, or GEM, detects the speed of ions coming from the solar wind. The Genesis Electron Monitor, or GEM, detects the direction from which the solar wind electrons are coming. Each monitor has a small door that opens to let particles in. Electrostatic analyzers then allow particles with a certain amount of energy to interact with the detectors.
The analyzer acts as a filter, allowing different energy particles to come in. They interact with the detectors, and we count how many came in that brief time, and we know how many of what energy, from what angle, the particles will have come in from. And using that information, we can build up a three-dimensional picture of the particle distributions and energies and directions they're coming from in space.
The data from the eyes and the ears, the GEM and GEM, are fed to computers. These computers act like the brain and make a decision about which hand to extend in the form of an array frame. This process optimizes the collection of solar wind. As with most of the instruments that fly into space, the monitors have to withstand a large amount of vibration, especially during the launch. Shake tests were performed on the monitors to ensure they could withstand full flight conditions.
One very important test that we do is called vibration test, where we take our instruments and strap them on to a very, very large speaker, and then we turn the loudest white noise on that speaker that you can imagine, and we shake our detectors. When you're shaking them, it doesn't actually look like they're moving very far. It looks very much like the blur you see on a speaker cone if you turn your radio up very high. But it puts a lot of acoustic energy into the detector. During the launch phase of the mission, when we're actually going from ground to orbit, the motors make a very, very loud noise and shake the spacecraft very violently. And so the vibration facility simulates that launch shaking. By simulating that launch environment, we ensure that we've designed an instrument that's capable of withstanding that shock of launch.
Other environmental tests include subjecting instruments to the conditions they may encounter in space. Thermal tests include operating the instruments in very high and in very low temperatures. In this test, a sample concentrator grid is being dipped into liquid nitrogen. Nitrogen liquefies at a temperature of -197 degrees centigrade. The difference between air at room temperature and liquid nitrogen is comparable to the temperature range the spacecraft will be exposed to on the sunlit side and the shaded side of Genesis in space.
What we wanted to check was to make sure that the tiny little grid wires did not themselves go through a phase change of the type of stainless steel that they are. And if that were to happen, there's a possibility that they could shrink an additional 10%, both in diameter and also in length, when they got cold. And you can imagine this would be rather catastrophic for the instrument itself. So under the scanning electron microscope, we got a very high power view of each of these grid wires, and we looked at them and carefully measured their diameters both before and after dipping in liquid nitrogen to make sure that they were not shrinking.
When tests cannot be physically performed, computer testing is an alternative. Los Alamos engineers built a computer model to accurately simulate solar wind. This model illustrates the ion trajectory trails of the solar wind on the concentrator.
This computer software is able to model the ion trajectories as they go through electric fields, as in a scientific instrument such as a concentrator. So we built up in the computer a simulation model of the concentrator. It uses 30 million different nodes or array points, and then we can fly in ions as if they're flying, and you can actually watch them on the screen and see where they end up.
Planning a mission to space must include thorough testing of all the instruments on the spacecraft. The many specialists at Los Alamos National Laboratory have developed tests for various components of the Genesis spacecraft to assure mission success. Los Alamos National Laboratory and the Genesis mission are working together to learn more about the beginnings of our solar system.